Bonjour, bon après-midi, bienvenue. Alors, the pleasure once again to greet you and to see you for this Ivado Quantum seminar once more. And this will be the last one of the semester, and for sure we're busy, completing the program for the after we return. A great pleasure to have David Gosset with us today. And you see, the title is collaborated, where he's collaborating with Sergey Bravyi, who was one of our last speakers. Let me introduce David. David is, studied, this is undergrad at UBC, if I'm not mistaken, and then went to MIT, where he did his PhD with another friend of ours, Eddie Farhi. And after that, I don't know exactly in what order. He was a postdoc at Caltech, at
Waterloo.
Waterloo, and he was at IBM also, or maybe he still is. No, all right. And now he's on faculty at at Waterloo in the math department, and also appointed to the perimeter. He's done amazing work in quantum information generally, and we're really thrilled that he's with us today to talk about the symmetric group and classical and quantum algorithms for that. So, David, thank you, and please.
Thank you so much, Luke, for the kind introduction and for having me here in Montreal. It's been too long since I've been in Montreal, and you've built a whole new campus here since I was last here. So it's amazing, um, and yeah, I'm very glad to be here. So I'm going to talk about joint work with Sergey Bravyi and Vojtech Havlicek, who are both at IBM, and Louis Schatzki, who was an intern at IBM at the time that this work was done. So the plan of the talk is kind of simple. I will give a kind of like fairly slow overview of the kind of group theory and representation theory that we're going to need. It's really not very much. And then I'll talk about classical algorithms and quantum algorithms, which are related to characters of the symmetric group. And I should maybe mention that I'm definitely not an expert in representation theory or the symmetric group, but we sort of came to this from a strange angle. We had a previous work that had to do with connections between computational problems related to partition functions of local Hamiltonians and representation theory of the symmetric group. And then we continued working in this vein, and that led us to this. So if you are interested in partition functions of quantum many-body systems, want to understand something about that connection, you can come talk to me later, and I can explain why we were looking at symmetric group and its representation theory. Okay, and I don't know how this works. Are people able to ask questions in the middle of the talk, or do you normally have it at the end, or? It's my choice. So I would prefer if you have a question, please go ahead and ask it. Okay. So as I said, I'm going to first talk about group representations. And so we're going to be in the setting of finite groups. And let me just remind you what a representation of a group is. For the purpose of this talk, we're only ever going to be speaking about unitary representations. And so what that means is that for every group element, we map it to a unitary matrix. So G goes to rho of G, and the dimension of that unitary matrix is the dimension of the representation. So we think of it as, there's some D by D unitary matrix for every group element. And the property of being a representation, well, we require that the group multiplication is respected. So rho of G times rho of H is rho of GH. Okay, so that is the kind of representation we're going to be talking about. That's the only condition. Yeah, it's a unitary matrix for every G. Okay. And such a representation is said to be irreducible if we think of the vector space that this matrix acts on. Yeah. Does it have to be one? Oh yeah, that's fine. Yes, that does respect this, and that would be called the trivial representation. Yeah, that's right. So this representation would be said to be irreducible if there's no non-trivial invariant subspace. So in other words, um, these matrices act on vectors of length d, complex vectors of length d, and if you have some non-trivial invariant subspace of vectors, we would say that that representation is reducible. And if there's not, then we would say it is irreducible. And obviously, there's a kind of basis change equivalence where I can take any representation and conjugate all the matrices by some unitary, say, and then I will get another representation. But up to that basis change equivalence, a finite group has a finite set of irreducible representations. So we can just talk about all the, up to basis change equivalence. There is some set of irreps, and we can talk about that set. Okay. We're going to need a little bit more. So for every group element G, we can think of its conjugacy class, which are all the elements obtained from G by conjugating with an element H. So H, G, H inverse. That's what we call the conjugacy class. And finally, we can talk about the characters, which is one of the words in the title of my talk. So what is the character? It's now a function from group elements to complex numbers, and the function is just the trace of the representation. So the character is associated with a representation, and it's just the trace of the matrices in that representation, okay? And you can see the reason why I have conjugacy class and character on the same slide is because the character is only actually a function of the conjugacy class. So if I take two elements that are in the same conjugacy class, the character evaluates the same thing. And the reason for that is because of the fact that rho of HGH inverse is equal to rho of H times rho of G times rho of H inverse, and because of cyclicity of the trace. Is that okay? So the character is a class function, we would say. It depends only on the conjugacy class. Any questions at this point? Okay. Yeah.
Is it required or that rho?
I believe that is required. I mean, sorry, it's a consequence. Excuse me. I believe that it's always the case that rho of the identity element is the identity matrix. Yeah. Yeah. Okay. Yes. Right. So now we're going to specialize to the symmetric group and discuss, what are these conjugacy classes and what can we say about irreps? And so we're going to just kind of set the scene, not in full generality of finite groups, but now specifically for the symmetric group. So the symmetric group is the group of permutations of the integers from 1 to n. And, I'm in a combinatorics department, so I can count the size of that set. It's, it's n factorial, as you know. Okay, so there's some other facts that we're going to need. And, I'm not going to try to prove these facts or justify them really, but probably many of you have seen these facts before. One of them is that if I have a permutation, I can always write it as a product of disjoint cycles. So let me explain what I mean. Here on the left, I have a permutation where 1 goes to 4, 2 goes to 3, 3 goes to 2, etc. So that's just telling you the image of every integer from 1 to n, which in this case is 6. But I could also write that as a product of disjoint cycles. And this notation on the right, what it means is that look at that first cycle. It says 1 goes to 4, 4 goes to 5, 5 goes to 1. The second one says 2 goes to 3 and 3 goes to 2. And the third one just says that 6 is left invariant. And you can see that this describes the same permutation as that. And it's always the case that for any permutation, I can write it as a product of disjoint cycles, just like that, okay? And if we forget about the numbers that are in those cycles and only just look at the length of the cycles, this permutation has one cycle of length 3, one cycle of length 2, and one cycle of length 1. And so the cycle structure, that's what I mean by cycle structure, it's described by a partition of 6. So it's a bunch of positive numbers that add up to 6. And I could equivalently, draw the biggest one at the top and then the second biggest and so on. So I can draw this kind of diagram that describes the partition. And that describes the cycle structure of this permutation. It does not uniquely specify the permutation, but it describes its cycle structure. But we were talking about conjugacy classes. Those are all, and for the symmetric group, the conjugacy class of some element, G, consists of all the elements with the same cycle structure. So the cycle structure labels the conjugacy class. Okay, so if I want to talk about conjugacy classes of the symmetric group, then what I'm talking about is partitions of N. Okay, so this is kind of a label of a conjugacy class. Is that okay? Okay. Now, I'm not going to construct the representations of the symmetric group, the irreducible representation, but I want to give you a couple examples. So Gilles also already mentioned the trivial representation, which maps every permutation to just the number 1. So that would be a one-dimensional representation. And of course, it's irreducible because there's no non-trivial subspace of a one-dimensional vector space. Then we can think of another one-dimensional representation, the sign representation, which maps a permutation to -1 to the sign. The sign of a permutation here is defined to be the number of even cycles in its cycle decomposition. And again, it's irreducible because it's one-dimensional. A representation you're probably most familiar with, or certainly you are familiar with, would be we're going to map a permutation to the n by n permutation matrix, which has a 1, 1 in every column, and that describes the permutation. That would be an n-dimensional representation, but it is in fact reducible. Okay, but actually, who can tell me a non-trivial subspace of this n-dimensional vector space that is left invariant by the permutation representation? Yes. All ones vector, exactly. So you can see, because if I act with on the all ones vector with any of these matrices, I get back the all ones vector. So that is an invariant subspace, and therefore this is a reducible representation of the symmetric group. Okay. Right. So we already talked about how conjugacy classes of the symmetric group are labeled by partitions of N. But it's also true, and we're not going to justify this in any way because we won't need to, but it's also true that the irreducible representations of N are also labeled by partitions of N. So for every partition, there's both a conjugacy class and an irrep of the symmetric group. And we're not going to need to construct them. It's just helpful to know that that is the case. All right. Okay. Yeah. Right. So, well, if you have a non-trivially invariant subspace, then it sort of means that the representation can be decomposed as a direct sum of two other representations of smaller size. That's the sense in which we mean reducible. Does that make sense? Okay. Okay. I want to just do an example here to make sure that we're all comfortable with this. So we're going to talk about the permutation group on 3 elements and on integers from 1 to 3, S3, and there are 6 elements of that permutation group, and I've written them in their cycle decompositions here. And if I wanted to group these by their conjugacy class, then there's only 3 conjugacy classes, right? There's one that corresponds to 3 cycles of length 1, there's a cycle of length 2 and a cycle of length 1, and then there's a cycle of length 3. So this is the 6 permutations of 3 elements divided into their conjugacy classes. And I also told you, but did not justify, that the irreps are also labeled by partitions of 3. So if I wanted to put irreps as the rows in this little table, I would have also the same partitions labeling the rows. Okay, so the columns here are going to be conjugacy classes, and the rows are going to be irreps. Okay. And then what should I fill out in the rows of this table? Well, I'm going to put the characters. So for each of these irreps, for every row, there is a character corresponding to that irreducible representation, and its value is the same for all elements in a given conjugacy class. So I can just put the value for that conjugacy class in the corresponding entry of the table. So looking at this, which representation gives me the character, like what is that representation at the top? Can anyone tell me what it is? That takes 1, 1, 1, the value 1, 1, 1? It's the trivial one, right? And what about the one in the second row? It's the sign representation, okay? Because it's -1 to the number of even cycles, okay? And then the third one, well, it's just some other representation that we didn't construct, okay? Irreducible. Now, this is called the character table of S3. And you could think about doing this for Sn when n is larger, and of course you'd have a much bigger table, okay? Does anyone notice any like funny features of this table that you might not have expected? Yeah, the columns are orthogonal, so that's a funny one, but we're not really going to talk about that. But there is one other funny feature. Yeah. They're all integers, right? That's a little bit funny. There's no reason they have to be integers. We're talking about the trace of a unitary matrix, right? So there's no reason it has to be an integer. And in fact, it is a kind of non-trivial fact that irreducible characters of Sn are integer valued, but it is non-trivial. I actually don't know how to prove this, but it is a fact, okay? I told you I was not like a representation theory guy, all right? All right. Okay. How can we compute the character? So here now I've introduced this notation where chi lambda of G, lambda is the irrep, and G is the group element or conjugacy class, okay? So how can we compute chi lambda of G? Well, there's various ways to do it that are in the literature. The most famous way is this thing called the Murnaghan-Nakayama rule. By the way, I'm not going to really explain any of these, but I want to just give you a taste of what they look like. The Murnaghan-Nakayama rule, it can be written as a recursive sum, but basically it's a sum of exponentially many variables, each of which is plus or minus 1. Okay, so from that, obviously you can see that it's an integer, but then, how do you justify this? Okay, so there's also something called the Frobenius character formula. This is an interesting one that we will discuss in more detail later in the talk. In this Frobenius character formula, we construct a multivariate polynomial that depends on G, and then we look at the coefficient of a certain monomial that depends on lambda, and that coefficient is going to be chi lambda of G. And then there's something called Reuteman's rule. This should say sum, not average, but it's also a sum of some plus, minus 1, and 0 valued variable. And so a natural question is like, how hard is it to compute chi lambda of G? And this is maybe, okay, so it's very hard. The problem of computing chi lambda of G, it's an integer, so you can just compute it. You can imagine the problem where you're given lambda and G and you want to compute that integer. And that problem is Sharp-P hard, which means that it's very unlikely that there is a polynomial time algorithm. But Sharp-P hard is sort of even harder than, we think of it as like even harder than NP. And actually, this reference, Hepler from 1994, is a master's thesis from the University of Calgary, is the original reference for Sharp-P hardness of the symmetric group characters. So I think that's an impressive master's thesis. This second line, it says that the problem of determining even just whether or not it's greater than or equal to 0 is PP complete. You should think of PP as being very similar to Sharp-P in terms of complexity. So it sort of says that even just determining the sign is like Sharp-P-like in its complexity, okay? And so if you think about that, it's sort of like even computing a relative error approximation would be just as hard as hard as class PP, which you can think of as being like Sharp-P. Okay, questions about this? So hopefully by now we've kind of told you a little bit about the representation theory. So now you at least sort of understand what the definition of the characters are. And then I told you those are like really, really hard to compute and probably the interpretation of all this is that we're stuck with exponential time algorithms in the worst case. So then you must probably be confused about what the rest of the talk is about. And well, I guess you're going to find out. Okay? Yeah, go ahead. It doesn't matter because, from the element, you can easily compute the conjugacy class. It's just this. No, well, okay, so um, no, because we're talking about a permutation of n elements. So I can just say 1 goes to 5, 2 goes to 7. Right, but if you fill it in with numbers, it's only like we're talking about a polynomial in n. That's our metric, right? So the description of a permutation has, I need n integers to describe a permutation because I just need to tell you the image of each integer from 1 to n. Maybe I could, yeah, we can, yeah. Okay. Other questions? Okay. Oh, I should mention that, this is about exact computation, or the second statement here is about relative error computation, determining the sign. But if you normalize, so remember that this character is the trace of a unitary matrix of dimension d. So it is upper bounded by the dimension of that representation of that era. And so if we divide by the dimension, we get a number whose magnitude, a complex number whose magnitude is less than or equal to 1. And this thing can be additively approximated to some given inverse polynomial error in polynomial time on a classical computer. So a normalized character can be additively approximated, but that is only useful if chi lambda is not much smaller than d lambda. The typical situation is that the dimension is exponentially larger than chi lambda. And so this is 0 to within a inverse polynomial error. So that's kind of like a strange situation in which this kind of additive error approximation might be useful. Okay. Oh, right. So now I guess my goal in the next few slides is to tell you about a recent work of Crichigno and Prakash, which we, in our paper, we explain in a different way. And I'm going to give you our explanation, but essentially this leads to a way of expressing symmetric group characters in terms of a system of fermionic particles that live on the unit circle. So I want to tell you about that. Okay. So we have our unit circle, and okay, if we have one fermionic particle, or just if it's just one particle, we don't have to think about it being a fermion. A particle living on the unit circle, the continuum, you can think of its wave function as a function of position on the unit circle. And because the unit circle is periodic, the momentum of that particle will be quantized. So like its wave function could be like it could be like e to the phi k, where phi is like the angle along the unit on the unit circle. But k has to be an integer, right? Because it has to come back to itself when phi goes from 0 to 2 pi. So momentum on the unit circle for a single particle is quantized. And so we can just label the momentum states of a single particle by integers, okay? But then if we have like more particles than one, like say we have n particles, and then it matters whether or not they're fermions or some other kind of particle. And if they're fermions, then what we should do to construct the n particle wave function is we should choose n different momenta, because for fermions, no two can have the same momentum. You choose n different momentum, and then anti-symmetrize we take the product of those momenta and then anti-symmetrize. That will give us an n particle fermionic wave function. Okay. But what this describes is just n particles with momenta k1, k2 up to kn. All the k's are different, and they're all integers, and the particles are fermions. So that is how we would construct an n particle wave function in first quantization. But another way of describing this, we could use second quantization. And what I mean by that is let's just think of our states like the k's as living on the line of living on the grid of integers. Okay, so in second quantization, we would have like an infinite grid describing the integers. Those are the single particle states. So the single particle states in this picture would just be like computational basis states corresponding to all zeros and then a 1 in one position, telling you which momentum the single particle has. Is that okay? And then in this second quantization, an n particle basis state would just be a computational basis state with n ones describing the momenta that, k1 through kn. Is that okay? All right. So that's what I mean by a system of fermionic particles moving on the unit circle. And I promise that we will soon connect this to symmetric group characters. Right. I am immediately going to truncate the Hilbert space of this infinite. In the second picture, I had an infinite chain of qubits, but I'm going to just think of truncating that chain, giving an upper bound on the magnitude of the momentum that I'm going to consider. And that won't introduce any error, and you'll see why later, okay? So I'm going to consider just a fixed number of qubits, which I'm going to take to be twice n. And I'm going to, since I'm working with qubits and second quantization, I can define the fermionic creation and annihilation operators via the Jordan-Wigner transformation. So these are operators that, acting on the vacuum, create a single particle momentum state with momentum k. Okay, they create starting on with the all zeros string, these create a bit string of weight 1, but they also satisfy the canonical anti-commutation relations for fermions. Okay, and the last ingredient I'm going to need before I tell you how this is all connected to symmetric group characters is this thing called the current operator. What is this? It takes a state of momentum, any momentum, like m, and then it kills the momentum m and increases it by L. Okay, so this current operator, it on any momentum state, it boosts the momentum by L. L is an index, so there's a current operator for every L. Okay? Okay. Are there questions at this point? We've got a few ingredients, and now we have to put them together. Okay. Yeah. N? No, n is the number of momenta that we're, like 2n is the number of momenta that we're considering. Because remember in the second quantization, every qubit is a possible momentum, right? Like 4 corresponds to momentum 4. So yeah, the number of sites is just the number of possible single particle momenta. Does that make sense? The Hamming weight of the computational basis state is the number of fermions. Yeah. Yeah. Mm-hmm. So the wave function is like e to the I phi k, where phi is the angle. So I think you call that maybe angular momentum. Yeah. Yeah. Oh, yeah, that's right. Because you're too near the boundary, so those ones don't get boosted. That's right. Yeah, that's a fair point. Yeah, so it boosts some of them, but not the ones that are too near the boundary. But the thing is that you're going to see that this truncation is a little bit annoying, but I promise that if you just think of everything as being infinite, then you don't have that problem. And the things near the boundary will everything is going to happen far enough away from the boundary that those boundary effects cause zero error. So you can, if you like, just think about it as being the infinite current operator. Yeah. Okay. Okay. So now here we are going to put some things together. So let's consider a group element, permutation, G, and let's say that its cycle structure is described by a partition of n, which is v1, v2 up to vc of g, where c of g is the number of cycles. Okay, so like in that example that we did before where we talked about conjugacy classes, it was like 3, 2, 1, right? But here it's like v1, v2 up to vc of g. Okay, that's the cycle structure of g. And so now what we're going to do is we're going to construct a state from the permutation. And the state is a state of 2n qubits. And what we do is we start with the computational basis state, which has n ones followed by n zeros. And then we apply a current operator for each of the cycles. So the first one is JV1 that boosts the momentum by V1. Then we boost it by V2, and then all the way up to V, the last cycle, C of G. Okay? So this is some state that depends on the permutation G. And the claim, which is proven in this paper by Crichigno and Prakash, is that if you look at this state, which is a 2n qubit state, and now you look at all the non-zero entries in the computational basis of that state, all of them are equal to the characters of like chi lambda of G. So G is fixed, but lambda varies over all the irreps of Sn. Okay, so every irrep of Sn evaluated at G is an entry of this state. And every entry of that state is an irrep evaluated at G. Okay? So I will give you a sketch of the proof in a moment. But does it make sense? Yes, so that's a great question. So which entry corresponds to which? Yeah, so that's my next. Okay, I'm going to answer that in 3 seconds. The first thing I'm going to say is that notice that because it contains all the characters for a fixed group element or equivalently fixed conjugacy class, this state corresponds to a column of the character table. It has an entry for every irrep. Okay. Now, getting back to your question, in particular, if we expand this state in the computational basis, it can be written as a sum over partitions lambda, chi lambda of G, and then the basis state that sits in front of is actually an encoding of lambda, the partition, in binary. And I have to tell you what that encoding is. Okay, there is some encoding of partitions of n into bit strings of length 2n, and that, if you understand what that encoding is, then you can read off the entries corresponding to a given partition or a given character. So the encoding here is very simple and quite intuitive. Here it is. So you will understand it completely by just looking at this example. Let's think of the partition lambda, which is 4, 3, 1. Okay, remember that labels some irrep. And what we're going to do is we're going to draw an n by n grid, and then we're going to draw the partition. So we draw 4 boxes, then 3 boxes, then 1 box. Okay? And then we're going to start at this bottom left corner, and we're going to put a 1 every time we go up, and a 0 every time we go across. And then we just follow the boundary. And that gives us a bit string of length 2n. So this is the encoding. Now, any questions about that? Yeah, there are other ways to encode, but this is the one. Yeah, so so maybe one observation that's part of your question is that the number of partitions of n is vastly less than the number of bit strings of length 2n, even if we consider the fact that all these bit strings have weight n. So like this is not a very compact encoding, but this is the one that is relevant to this theorem that I just told you. Any other questions? Yeah. Yeah, so you start down here and then go across like that. Does that make sense? Yeah. Okay, so that's the encoding. Right, so now I want to give you a kind of this is not the proof in Crichigno and Prakash's paper, but we realized, and the kind of first thing in our paper is just, we realized that this theorem really is just a reinterpretation of the Frobenius character formula. And maybe the right way to say it is that the Frobenius character formula, which is very old formula for the characters, actually is kind of like naturally phrased in terms of fermions. Okay, so let me tell you how that works. And I'm not really going to write down even the Frobenius character formula, but I will show you the sense in which it gives you this theorem almost immediately. Okay, so this is a little sketch. So how does it work? What is the Frobenius character formula? As I said, I'm not going to write it down completely, but I want to tell you that it has this form. So it says that if we're interested in the character chi lambda of g, what we should do is look at a polynomial q g of z. So this is a polynomial that depends only on g. And the polynomial starts with this kind of funny product of zi minus zj. Here m, there's like m variables zi, right? And m is the number of parts of the partition that we're going to care about, okay? So we're going to start with this kind of funny product of zi minus zj for I less than j all the way up to m. And then we're going to apply some operator p sub g that depends only on g. Sorry, not operator. We're going to multiply that by another polynomial of these variables z1 through zm that depends only on g. And then we're going to expand that as, you know, some sum of monomials with coefficients, right? These are just like polynomials, right? So you expand it, write it as a sum of monomials. And then what we're supposed to do is find the coefficient of that monomial that depends on lambda. Okay, so lambda 1 through lambda m are the parts of the partition. Okay, so this, it just says like construct this polynomial that depends on g, find the coefficient that depends on lambda. And then that will give you that coefficient is the character that you care about. Okay, why is this fermionic? Yeah, go ahead. Okay. So, right, so now what I said is we're supposed to consider fermionic particles moving on the unit circle. And like I said before, the wave function of a single particle momentum state is z to the k, where z is a complex variable that lives on the unit circle. It's e to the I phi. So this is z to the k is the wave function of a particle with momentum k. So given that that's the wave function of a particle with momentum k, oh, I was going to ask you what this is, but now I've told you what it is. So this thing here is the wave function of a Slater determinant state of m fermions. So this is the state this is the anti-symmetrized state of fermions with momentum m minus 1, m minus 2, all the way down to 1. And that is a non-trivial fact that this is equal to that. And to see that, you need to use this van der Maan determinant formula. But that is the wave function of this state of m fermions. So if you were to take these m fermions with those momenta, anti-symmetrize, you get that wave function. Okay. This thing P of G that I did not construct for you, it is, I mean, I guess I'm just not constructing it, but if you were to construct it, you would see that it is a current, it is the current operator, okay, in this language. It shifts the momenta depending on G. And finally, this thing here, this wave function, this thing, the coefficient, this monomial that we care about, it's the wave function of a product of single particle momentum states. But if you were to look at like this thing this polynomial that we're going to expand, the coefficient of that monomial, if you look at kind of the symmetry of this polynomial, the coefficient of that monomial is the same as the coefficient of the anti-symmetrized monomial. So we can think of that as like we're taking an inner product with another Slater determinant with momenta lambda 1 plus m minus 1, lambda 2 plus m minus 2, and so on. Okay, so in other words, the blue, the green, and the red can be converted directly, if we go to second quantization, into these states and operators, okay? And now Gilles is making a face, and there's many reasons he might be making a face, but one reason might be that m turned into n which is pretty pesky, right? Like in the previous thing, there was an M, and now we have N. And let me just explain what that is. The reason is that M was the number of parts of this partition, but that is always upper bounded by N, which is the, the integer, the symmetric group Sn. So here we're doing truncation of the Hilbert space so that we always, if we only ever care about M less than N, we always can upper bound it by, we can always truncate the Hilbert space in this way. Sorry, that was a little bit. In other words, we pad, if we have a partition with M parts, we can pad it with a bunch of zeros, and then it sort of, you think of it as having N parts, where N is greater than M. Is that okay? Okay, so the point of this is just the Frobenius character formula. You think it just is this formula. Just you just have to do second quantization. Okay. All right. Okay, so that was the first part of my talk. And then we're going to talk about classical and quantum algorithms. And so are there any questions about this so far? Algorithms to do what? Great question. And there's not just one answer to that question. We're going to do a couple of different things. Yeah. Okay. So first, we're going to talk about classical algorithms. And here, okay, so we have rephrased the problem of computing symmetric group characters to the problem of computing entries of a certain quantum state. And what is special about, what do we know about quantum states that everyone else doesn't? Like, well, nothing, but what are we good at that, maybe outside of quantum information, people are less good at or less familiar with? Well, one thing is entanglement, right? And so what we could hope to do, what we could hope is we could hope that this state actually has low entanglement. Like this is a state of a spin chain, right? Like we have 2 n qubits in a chain. And we might hope that most of the time, if you take a cut between qubit I and I plus 1, maybe there's like not very much entanglement across that cut. And if that's the case for all the cuts, then what you can do is represent this state as a matrix product state, which is, much more efficiently describable than a general state of 2 n qubits. Now, of course, that's not really going to work in the sense that we can't get an efficient algorithm for symmetric group characters because we know they're sharply hard to compute. So the best we're going to hope for here is just a heuristic algorithm that, or an algorithm that does better in practice than existing algorithms. That's the most we could hope for here. So what is our goal? So I said represented as a matrix product state. That is the kind of state that I mean that has low entanglement across any bipartition of the qubits. And specifically what I mean is that such a state, every entry can be written. So here Z is a bit string describing of length 2n that describes a computational basis state. And the inner product between that computational basis state and psi G should be represented as matrix vector product, where these matrices, for every Z1, Z2 up to Z2n, we have a matrix M1, M2 up to M2n. And we take the product of those matrices and sandwich them between 2 vectors U and W, okay? This is what I mean by a matrix product state. It's something where the entries can be written in this way, where these are matrices for every fixed value of the Z's. And in fact, every state can always be written this way, but the good situation, the situation where you have low entanglement, corresponds to the dimension of these matrices being small. Okay, so we're interested in the case where these matrices can be taken to be like D by D, where D is not, root n or something, root 2 to the n, where D is like much smaller than that, say maybe polynomial n or something like that. That's the case we're interested in. Because if D is small, like what is the computational cost of computing this kind of matrix vector product? Well, we have to multiply n D by D matrices. So the cost of computing a character, if we had this kind of representation, would be n times D squared. So we want D to be small. Does that make sense? Okay. So the first thing, was there a question? Okay. So the first thing we're going to do is we're going to write the state psi G exactly as a matrix product state, but then these matrices are going to have a large dimension, and then we're going to talk about how to reduce the size of those matrices, okay? So in order to do that, we are going to express the current operator. Remember that the state is built from a product state by applying a sequence of current operators. And what we're going to do first is we're going to take these current operators and write those as what we call matrix product operators. Those are matrices with the following form. So you have you have a tensor network with legs going up corresponding to the right multiplication of the matrix, and legs coming from the bottom, that's like the right side, and legs at the top, which correspond to like multiplying on the left. And okay, I am hoping that I know that I should not ask you to parse this, so I will not ask you to parse it, but I'm hoping that people are generally reasonably comfortable with this notation at least. So the claim is that this current operator, which I've written at the top using Jordan Wigner, can be expressed as a tensor network built from these little TL tensors. TL is a tensor where the legs on the right and left act on a vector space of dimension L plus 2. So those are, tensor legs of dimension L plus 2. So we can connect it, for example, to any integer between L plus 1 and 0. So on the left we have 0, and on the right we have L plus 1, and then we take the contraction of the tensor network that way. And, at the top and at the bottom, those legs correspond to the qubits, right? So those are 0, 1 values. And the claim is that this is just an exact tensor network representation of the current operator. And the bond dimension is L plus 2. That's this dimension of these legs. And here L is the momentum that we're boosting by. Okay, so J sub L has this bond dimension L plus 2. And this is an equality. There's no approximation here. And once you have this, then it's very easy to build a tensor network for the state that we care about that encodes all the characters. Because what we do is we start with our, I'm in orange, I'm drawing like what we've built so far. Okay, so far we've built all ones and all zeros. That's just written down here. And then we connect that to the tensor network that applies JV1. Remember, V1 is the cycle length of the first cycle in G. And so we connect this leg to that tensor and this leg to that vector and so on. And now, like, this describes a tensor network that describes the state JV1 acting on all ones followed by all zeros. And the bond dimension here is at most V1 plus 2, because remember that the bond dimension of this matrix product operator across that cut is at most L plus 2, and L here is V1. But now we can just do the same thing for JV2, and we connect that to this tensor network. And now we can think about what is the bond dimension across this cut. Well, the way tensor networks work is it's the product of this and that. So it's at most V1 plus 2 times V2 plus 2. And then we can just keep building our state. And once we've applied all the current operators, we get psi sub G. And now the bond dimension across any cut is like the product of all the cycle length plus 2s. And we can combine all of those in these columns into one matrix. And then we get our matrix product state representation, which in this case is exact. Okay, so there's no approximations here. And so in that way, we can prove a theorem which says that the group character can be written as an entry in the computational basis of a matrix product state whose bond dimension is upper bounded by the product of Vj plus 2, where Vj are the lengths of the cycles in the cycle structure of G. But, and of course, that will scale exponentially in n. And so that's why this is not, breaking complexity theory. So this gives an algorithm for computing characters with runtime n to the number of cycles. But you might ask, I said we were going to try to use our knowledge of entanglement, and so far we haven't really done that. So how are we going to do that? Yeah, and And really, we were interested in like, is it possible to make this competitive in practice with other algorithms? And so what we did is we used the fact that symmetric group characters that I told you before are integers. So there is actually a sense in which we can tolerate some level of approximation here. Because if we have another state that approximates, some other matrix product state that approximates psi g, then if we compute the entry of that other state, and it's like within 1/2 of the group character, then when we round that entry, we're going to get the group character. Okay, so because these entries of the state are integers, we can screw them up a little bit and round, and then we'll get the right thing. Okay. All right, so then we use a kind of very, very well-known technique in matrix product states, which is that that it's always possible to, let's say we fix a cut between I and I+1. There's a way of finding the best, rank K approximation of the reduced density matrix, if you like, or the best way to truncate the Schmidt vectors across that cut to rank K. The way that you do it is you do the singular value decomposition, which is the same as the Schmidt decomposition, and throw away the Schmidt coefficients that are very small. And you can do this kind of recursively across all the cuts. And so there's kind of a way of taking a matrix product state and an error epsilon and truncating an epsilon fraction of the Schmidt coefficients across every bipartition. And that's kind of a standard way of compressing matrix product states that is used in condensed matter physics and other places. And so you could try to use this algorithm, to make a matrix product state with even lower bond dimension that hopefully also includes the symmetric group characters. So what is the algorithm? The algorithm is we're going to start with our all ones followed by all zeros. We apply the first current operator. Then we compress that using some epsilon error. We truncate an epsilon fraction of the Schmidt coefficients across every cut. And then we apply the second current operator, and then we do the same thing. We compress, and then we keep going. And the question is, does this actually help us at all? Using this trick, will this help us? And so here's some numerics that were done by my collaborator, Sergey Bravyi. He found that okay, so these numerics compare this matrix product state algorithm with a very small compression error, 10 to the minus 10, with computer algebra packages GAP and SAGE. And he tried to find characters that were harder to compute, and he found that like smaller cycles seem to be harder, like characters that have many small cycles. And so this is some permutations that are composed of n/2 length 2 cycles and all irreps. And you can see that the blue, which is our algorithm, is competitive and in some cases better than the GAP and SAGE algorithms, which are, I think, fairly optimized. Now, with this compression error of 10 to the minus 10, this number that, this final rounding, when we do the rounding, we could be half off by an additive factor of a half in every entry. But in fact, we're only off by 10 to the minus 6. So we're very, very close. But nevertheless, that rounding with 10 to the minus, or that compression with 10 to the minus 10, it makes our bond dimension is a lot less than the maximum, than what it could be. Okay, so we are saving something here. Okay, so that answers Jill's question of what is the classical algorithm. Okay, that's the thing that we propose. And none of us are, as I said, we're not like experts in representation theory, and we're certainly not experts in what the algorithm is in SAGE or GAP. And so, we're not carrying this forward as something to be like included in Maple, or, this is not we're just proposing this algorithm that we think is interesting, this connection between entanglement and characters, and hoping that it is interesting to others. Did you have a question? Mm-hmm. I don't think we know how to do that. No. Yeah, I mean, it would be nice if you could do that. Yeah. Yeah, you can think of this as really just more of a study so far, a numerical study of like what is the entanglement in this state that how much error can we how much can we truncate the entanglement of the state that encodes all the characters without corrupting it? That's so far what we've investigated, I guess. Yeah. Yes. Um, I think it's the same question. Like yeah, the question is, can we rigorously bound the total error? I think not. Yeah, I think maybe not. Yeah. Okay. All right. So that brings me. Okay. So the summary so far, and I'm probably running out of time. I have 20 minutes. Perfect. Summary so far is that this state that is like this spin chain thing that encodes all the characters for a given conjugacy class G or group element can be approximated by a matrix product state. And, that seems to lead to a competitive classical algorithm. Okay. And the next part of my talk is about quantum algorithms. And so let's answer Gilles' question again. What quantum algorithms for what? It's going to be a quantum algorithm for something different that is related to everything that I've told you. Okay. It's not a quantum algorithm that also computes characters exactly. This state that we've been talking about, the first thing that I will say is that remarkably, for any group element G, there's an efficient polynomial n time quantum algorithm that prepares that state. Okay, so that's kind of interesting. So remember, this is a state corresponding to a given column of the character table. And the second statement is that we could construct a state where we fix an irrep lambda and sum over all the entries of the given row of the character table. And the second statement is that for any irrep lambda, there's also an efficient quantum algorithm that prepares that state. Okay, now these, the ability to prepare these states does not give you an algorithm for computing group characters. Okay, but sorry? Oh, excuse me. Yes, this symbol lambda, kind of this sideways Tn, that means that lambda is a partition of n. Other questions? Okay, so like I said, these algorithms are not useful for computing characters, because if you wanted to compute a character in this way, what would you do? Maybe you would measure the state, but then you would get chi lambda of G over the normalization of the state, chi lambda G squared, if you were estimating the output probability to some invert. I'm explaining some imagined algorithm, but the point is that there's no good way to get the characters out of the state. Okay. What's that? Well, if you what you could do, for example, is you could measure repeatedly and count the number of times you get some outcome, and then but that's going to be a bad algorithm. Yeah. Okay. So, and these algorithms, which I was going to explain, they are a kind of simple application of the quantum Fourier transform of the symmetric group. So it is a fact due to Beals from 1997 that Fourier transform over the symmetric group can be done. The quantum Fourier transform over the symmetric group can be performed efficiently on a quantum computer. And using that fact and some other tricks, we can prepare these states. The second one, there's really very few other tricks. The first one, there's a little bit more. But then you can ask, is there a quantum advantage based on doing something with these states? And I want to comment a little on that. Yeah. So when Gilles asked, what are these algorithms for? There's not an entirely clear answer here. There's a proposal, but it's not. Here, the algorithm is for state preparation, and what you can do with it is maybe a bit of a question mark. Okay. Right. Now, I think that we go until 2, but it's supposed to leave time for questions. Is that right? Yeah. I'm roughly at time. Okay. So I will then, in that case, skip over the description of how you can prepare these states using the quantum Fourier transform of the symmetric group. But you can ask me about that later. And I will, maybe if I could take a couple more minutes, I will just talk about what maybe we might want to do with these states. Right. So one thing you can do with this row state or the column state is you can measure in the computational basis. And if you do that, then in one case, you'll be sampling, well, we call this column sampling, and that's sampling from a distribution that's just the measured distribution of the column state, and the row sampling is like sampling from the measured distribution of the row state, okay? And you can ask, is there a classical algorithm for sampling from these distributions, okay? And, you know, there's other problems in quantum computing, like, for example, sampling from the output distribution of a random quantum circuit that we believe are hard for classical computers. But those, first of all, there's a few caveats there. One is that we don't know how to prove they're hard for classical computers. That's the big caveat. And there's many other caveats, like what, you know, why is that, why should we care? But putting aside that second thing, we don't know how to prove that sampling from, say, the output of a random quantum circuit is hard classically. We might hope that these distributions have a similar classical hardness. And that's something that we were interested in and that we investigated in this paper. And what's nice about these distributions is that they have additional algebraic properties. So it's not like a random quantum circuit, the output probabilities of a random quantum circuit have no algebraic structure. But here, every output probability is like an integer squared divided by some normalization, right? Like look at the second distribution, integer squared over n factorial. And so we kind of hope that that algebraic structure maybe could help us to prove some of these conjectures about classical hardness. And in particular, like the algebraic structure that we tried to use here, it's very funny. If you can come up with other examples like this, I'm very interested, okay? So in this example, let me tell you what's funny about this distribution. This is a distribution over, we can think of this as a distribution over group elements G, and there's n factorial of those, okay? And the, so the size of the sample space is n factorial, but every entry is an integer over n factorial, and they're all positive. So that doesn't make any sense unless many of them are zero, right? Many of these have to be zero for that to make any sense, because it's an integer over n factorial, and there's n factorial things, and they sum up to 1, right? So all probabilities are integer multiples of 1 over n factorial, and we have a sample space of size n factorial. That can only happen if many of the probabilities are 0. This we would call granularity, okay? This property. Actually, we generalize it slightly. So we would allow some multiple of some constant gamma over the size of the sample space. We would call that a granular distribution. And we show that, so okay, so this is showing that the row sampling distribution is granular, but we also in our paper show that the column sampling distribution is granular for most columns of the character table. And then, just to wrap up quickly, then we show that if you have a sampling problem that is granular, admits an efficient quantum algorithm, and for which you can show a kind of average case classical hardness. And what I mean by that is that the problem of computing an output probability exactly at some random entry, x, that should not be contained in this polynomial hierarchy. So think of this, another way to, if you could show that that was sharply hard, that would satisfy this, this condition 3. So we know that computing group characters in the worst case is sharp p hard. And here we're trying to say that in some kind of average case, it should also be sharp p hard. And so that's the thing we don't know how to prove. But if you could prove that, then this would all come together and we would get this, this theorem, which says that if there was a classical efficient algorithm for the sampling problem, then the polynomial hierarchy would collapse. Okay, so this, if you have not seen these kind of quantum supremacy arguments before, this might be a bit mysterious. But the aim here is to understand whether or not we can establish classical hardness for sampling from these row and column distributions. And the hope is that the algebraic structure of those distributions helps us in a way that we're not helped in the random circuit sampling case, where we have a lot of conjectures we don't know how to prove. Okay. And what are the prospects for that? Well, for row sampling, it doesn't seem like it satisfies these conditions. Column sampling, we don't know. Okay, the average case hardness is a question. And I will end there. We have some extensions and open questions, and you can have a look at our paper for those. And I'll thank you for your time.
Thank you very much. Questions? Okay, nobody has a question? Ivan, I feel you have one.
The idea of
Yeah, so well, for the quantum case, you would need a quantum Fourier transform over those groups. I don't know the answer to whether or not we have a quantum Fourier transform over those groups, or let's say the alternating group. Yeah, I think just people have not really looked at this. It's a good question. Yeah, but again, I think that may just be a function of the fact that we are not experts in any of this, and sort of that was the one that we could understand most easily. Yeah.
Wow, some people, you provoke me by talking about Kotzka numbers. Can you extend that, for instance, to the QT Kotzka, so the expansion of the McDonald functions over Schur functions? And I was wondering also for what was the role of the Schur functions in all that you've described?
Yeah, so for the Kotzka numbers, we do have an extension. I don't know what the QT Kotzka numbers are. So I think
so the McDonald polynomials, so symmetric functions that involve these two parameters, have also expansion coefficients on the Schur functions, and they involve these two parameters, and they have the property of being positive integer numbers. That's quite. It was a long time conjecture for proving that, and it connected to the n factorial conjecture. Was proved using fancy algebraic geometry, but it's a big challenge. So maybe you could just address what you have in mind with the Kotzka numbers that you're talking about here.
Yeah. I think I cannot answer that question. I think I would have to refer to one of my co-authors who
don't worry.
Yeah.
Any other questions? Okay, so people are mulling over what you told us, and there. Hey. Oh, like in order to compute the group character? Yeah, because, okay, so think about it. Like if I have a probability of a output probability of a quantum, say the probability of getting outcome 0 in some quantum circuit, and I want to estimate that. So then what I can do is I can run the quantum circuit some number of times, like n times, capital N, not the number of qubits. So I run it capital N times, and then I count the number of times I get 0 when I measure. And then the output probability should be like the count divided by n, the number of times I measure. But like the error in that estimate will be like 1 over square root the number of times that I measure. And so what you'll get here is you'll get chi lambda of g squared divided by the normalization of the state plus or minus inverse polynomial error. And so that's not, typically the chi lambda of g squared divided by the normalization will be exponentially small, and that will not give you any estimate. Like typically your count will be 0, is the point. Yeah. Does it make sense? Yeah. Any room to use AI to also learn about how to do these computations, how to compute these character tables?
That's a good question. I think that this matrix product state compression thing, there's obviously a little bit of heuristic there, right? Like we don't know how to bound the errors, and there's no, it's sort of like we're asking the question of like how much entanglement is there in this state that encodes the characters. Maybe that is something that could be learned by AI or understood better in some way by AI or predicted. That's my best guess. I don't know.
Well, I think there's really current investigations on those issues right now, but it's not understood. It's really a research question. Anyone else with a question? No, well then we will thank David for a very nice talk. Thank you very much. Thank you. I wish you all a happy holiday season because we're getting there, and we'll see you in the new year. Take care.